We are back at number 4. So an old medical textbook states that the mean blood sodium level for healthy adults is 142, and the mean blood sodium level here, units are milliequivalents per liter. So we'll go with that. And then a medical researcher believes that because of modern dietary habits, the mean sodium level for healthy adults, mu, now differs from that number that's stated in the textbook. So they take a random sample of 40 healthy adults and they're evaluated. The mean sodium level for the sample comes out to be 139 milliequivalents per liter. It's known that the population standard deviation of adult sodium levels is 11 milliequivalents per liter. Assume that the population is normally distributed. Can we conclude at the 1% significance level that the population mean sodium level differs from the one in the textbook? All right, so instead of saying test the claim, it says, can we conclude, same idea, can we conclude that the mean differs from what was stated in the textbook? All right, so let's start with our hypotheses. So our claim is that the mean is different than the 142 that was stated in the textbook. So when we have a case of a claim with a not equal to, this is a two-tailed test. The null hypothesis will always be the same thing, parameter, but now it's equal. So same symbol, but now equal, and same value, 142. Okay, so let's write all of our given information here. So mu naught is 142. And then they went out and took a sample N of 40 adults. The mean for the sample came out to be 139. The population standard deviation is 11. The significance level alpha they'd like us to use is 1% or 0.01. And then we are ready to convert our X bar into a Z-score so we can graph. So what we know right now is we're going to assume the null is true, and then we'll see if the evidence convinces us otherwise. And so for our evidence here, our test value is our Z-score that corresponds to that value X bar. And we can let the Z-test find this for us to save us a little work. So I'm going to go to my Z-test. And I've typed in those values. So making sure we have 142 for mu, sigma's 11, X bar 139, N is 40. And for the direction of the test, we want the not equal to. So mu not equal to our mu naught number. All right, I'm going to go calculate and just write down that Z-score. So it's negative 1.72. I'll stick with 2 decimal places. So that tells me on the graph where X bar 139 is. Okay. So I'm going to go ahead and do traditional method first. So before I graph that test value, I need to establish my critical region. So for a two-tailed test, we have our alpha. So alpha is 0.01. So for a two-tailed test, half of alpha will be on each side of the graph. So it's similar to a confidence interval. So we're going to take our alpha and divide by 2 for a two-tailed test. So that's going to be 0.005. So for our critical values, these Z-scores, there's going to be 2 of them, so we can write plus minus. And then you can just inverse norm. And alpha over 2 will be this area on the left. So we could just inverse norm the alpha over 2. And that'll give us the negative answer. And then we'll put a plus minus in front of it since we know that there will be two values for a two-tailed test. So let me go to my distributions and inverse norm, 0.005. And again, it's showing negative, but we know there's going to be two critical values for a two-tailed test. So plus or minus around to two places, 2.58. All right. So let me establish my critical region on the picture. So when you do these problems, you're going to want to just make a quick sketch and label your critical region so you can determine your location of your test value. So I always have you graph X bar and Z so you know what we're doing. We could actually skip the X bar axis and do everything with Z and still be okay. But I think it helps to see what we're doing by showing both. So let's graph our 2.58 and then I'll do my negative. So my critical value over here is approximating 2.58. So that area, that little area over there is going to come up here. So that area is alpha over 2. 0.005. So these z-scores make up the critical region. But then on the other side, our other critical value, negative 2.58. So there, that little area is our other alpha over 2. And I'm just coming up here to label my critical region. But that area is also alpha over 2. All right, so z-scores that are not out in those ends and the unshaded part would be in the non-critical region. Okay, so that's the difference for a two-tailed test. We have two critical values. We have two critical regions. And then everything is the same in terms of the traditional method. We're going to graph our test value. So that came out to be negative 1.72. So about there, test value, negative 1.72. That tells me that 139 will be there. So that's 142. So 139, that makes sense. It's to the left. So those two line up. So my 139 is in this unshaded region. So it's not out here in the shaded critical region. So my test value falls in the non-critical region. And that means we are not going to have enough evidence to reject the null. So it is different than 142, but it's not different enough. It's not all the way over here, not different enough to say that it's a significant finding. So when our test value is not in the critical region, we say we do not have enough evidence. We do not reject the null hypothesis. The evidence is not strong enough to make me reject that the mean is 142. Okay, so what you have to remember for a two-tailed test is you'll have your alpha, and now you want to make sure that you do alpha over 2 when you inverse norm. Now the p-value method is similar, but a little change here from when we did one-tailed tests. So let me actually go all the way down here. All right, so let's do our p-value method. So for the p-value method, not as much graphing. There's the 142. All you graph is your test value. So my test value is negative 1.72. But again, that tells me that 139 is there. So the area beyond the test value is our p-value. But because it's a two-tailed test, that area, instead of being the entire p-value, it's going to be just half of it. So that area is the p-value divided by 2. So it's similar to how up top, the two sides together here made up alpha. So alpha over 2 on each side for a total of alpha. It'll be the same idea here. Half of our p-value will be on this side. So how do we draw the rest of the p-value on the other side, the other half? So basically, there's only one test value ever. We already found it, the test value up here. There's only one test value ever. But in order to graph the remaining part of our p-value, we look at I call it the partner of this number. So if that's negative 1.72, positive 1.72 would be there. It's not a test value. I just call it partner, which is totally unofficial. It's just my made up word for the number on the other side. And the reason I need it is because when we shade our p-value, we have to make sure to shade this side as well for a two-tailed test, because the other half of our p-value is on that side. So these two areas together will be the area called the p-value. Just like those two areas together are the area called alpha. All right, so getting a visual here. I can see, because we've graphed it well, that if I look at my two purple areas here, those together are definitely bigger in size than these two little ones together. So my p-value area is definitely bigger than my alpha area. So I don't need the calculator to tell me that, because I'm looking at my pictures. My p-value area is bigger than my alpha area. And we know that that means when your p-value is greater than alpha, it meant that your test value was not in your critical region. And so I know that we don't reject the null hypothesis. So do not reject H naught. So the little rhyme again is, when your p-value is low, let the null go. But the p-value is not low. Low means lower than alpha. So when our p-values are not a low number, not lower than alpha, we do not reject the null. Okay, so let's confirm that all that is true here by looking at the numeric value. So I'm just going to go back to the test and just run that again. And I'll do calculate. And there's my p-value. So that's 0.0845. And that is bigger than 0.01. So I left it in decimal this time just to show you that you could. 0.0845 is bigger than 0.01. I just like to talk percents. So my p-value is 8.45%. So those two areas together would be 8.45%. We don't have to worry about what they are divided by 2. We're just looking at these two together. That's 8.45 compared to those two up top together are your alpha. So 8.45% is definitely greater than alpha, which was 1%. So my visual here matches my numerical values. All right. So the conclusion, so we're going to address this claim, and I'm just going to add up here then. We've just decided the decision was do not reject. So we decided we don't have evidence to reject H naught. And if you don't reject the null, then you do not support your claim. And that's our conclusion at the end. So that'll be our sentence here at the bottom. All right, so based on a sample of was 40 healthy adults, we'll just say 40 adults. 40 adults, we conclude there is not enough evidence to support the claim that the mean adult sodium level, and again, we say the claim exactly as it was stated and as we wrote it here. So the sodium level differs from that given in the textbook. So the adult mean sodium level differs from that given in the textbook. Okay. So there is your example of a two-tailed test. So the key is with the traditional method, you need to make sure you take your alpha and divide it by 2. For the p-value method, when you graph it and they ask you to shade the p-value for a two-tailed test, you need to make sure that you graph your test value, but also whatever its partner is on the other side symmetrically so that you have your other half of your p-value on the other side.